Hi everyone, welcome back to my channel. Today we're going to be going over ARIMA models. ARIMA models are super cool. They're very applicable to like almost everything that we do because we are all on the same timeline, and given our historical data, we are then going to try to predict something into the future based on our historical data. That's essentially what a ARIMA model is. If you haven't already, make sure you like this video and subscribe for future content. It's free. I upload videos every week on a Sunday, and also, the occasional Easter video during the week. So, without further ado, let's get back to it. Now, there are three components that an ARIMA model is based on. The first component is the autoregressive component, or the AR process. You can think of the AR process as a regression analysis. So it's very similar to linear regression. If you haven't seen my linear regression video, it's linked up here, so do make sure you check that out so that we are all on the same page. The second part, I'm skipping over the I, but the second part is the moving average piece. The moving average is essentially a dependency on the historical values, where essentially you're calculating the average within a given time frame, and then as new data comes in, you are deleting your older data so that you're accounting a new average. So every time more data is coming in, your average is always being updated. So that's where the moving average phrase comes into play. The third piece is the integrated piece. Now the integration, the only thing that's involved here is to make your data more stationary. When your I value is equal to 1, it just takes one difference of your data. So it's subtracting your future data with today's data, and that is your new difference data. So that's essentially what an ARIMA model is. We have three components. We got the autoregression, we got the integrated piece, and we have the moving average. We combine all of those components together and you have an ARIMA model. Now, there are like a little bit of other components if you're incorporating seasonality, but that's more so for like a different video. Without further ado, let's get down to the demo. I went ahead and I just downloaded data from Yahoo Finance. I obtained essentially 5 years worth of data, October 1st all the way to October 16th, 2015 and 2020. I got the adjusted closing value for NVIDIA. This is what we are going to be predicting. This is the stock price. This is just the volume of how frequently that particular company, NVIDIA, was trading at. These values over here are associated with the treasury rates and yields. And so I got the 1 month, 3 month, etc. I mean, all of those values in there. I also got the adjusted close for other competitors, so AMD, Intel, and Broadcom. So I essentially just downloaded all those data and put it into the same Excel spreadsheet, and now I am going to be reading it into here. And so this is what it looks like. Do a real quick summary, and this is what the head looks like. I have all my observations over here, and we do not have any NAs. Do note that I did some cleaning in the background on where there were some I guess like missing dates that were involved. So I just made the assumption that the values related to the data over here, the missing values were actually related to the yields within the treasury notes. So if there was a missing, I guess like row associated with the date, I assumed that the previous value was going to bleed onto the next following date that was missing. So I just copied and pasted that on over there. So do take that into mind. Okay, so I use the library XTS in order to create XTS objects. XTS is just for time series, essentially. This very first line I did over here, I converted the very first column of dates, and I shifted this date over to the row column names, or just row names in general. And I am going to be using the volume all the way down to adjusted close with Broadcom to help predict the adjusted close. I'm also going to be using the adjusted close as well. So let's actually take a look at what this looks like. This is what the adjusted closing price looks like for NVIDIA. There is a trend, a positive trend going down, and then we have some downturns in the market and some more downturns, one recent one, and it's going back up. let's take a look at the trading volume. This is what the trading volume is like for NVIDIA. So there's like 8 to the 10 times 8 times 10 raised to the 7. That's the trading volume on what this is going to be. But we are going to be scaling this down so that our data could be more adjusted to the overall algorithm that we are going to be using. The next step within the ARIMA process is that we are going to use a decomposition method. So I am going to be converting the XTS object to a TS object, which is just time series. It's just a different object, different nomenclature over here. And I'm just going to be doing this on the adjusted close, where I will set the date, the start date and the end date from 2015 of the October to 2020 of October. The frequency is just the number of days or number of periods within a given year in this case. So there are about 251 to 252 trading days within a year. So I just put this to 251 and just walked away from that. So we have this, and we calculated our components with the decompose function, and let's plot that. So one of the really neat use cases of this is that we can actually identify whether or not this time series is going to be additive or multiplicative. The additive is essentially very similar to that of a linear regression, on where we have beta naught plus beta 1 times x1 and etc. plus your error. Whereas if you want to do a multiplicative type model, you'll be multiplying the beta coefficients together, like beta 1 times beta 2 times beta 3, etc. So that's the only difference between multiplicative and additive. So in this case, I'll be doing an additive time series. Our very first graph is just a regular plot of our data over a period of time down here. And the second graph is just a trend, if it's upward trending or downward trending. Very useful insights. We have possibly seasonal variations on where we could potentially apply this to our given model if we want to do a ARIMA. And we have our randomized values over here, where our time series could not decipher what this, I guess, noise is. It's data that cannot be explained. So the very next step is that we are going to try to determine whether or not we need to achieve stationarity, or stationary, whether or not the data is stationary. And one of the primary visuals that we need to get this very first plot is to make it so that we have like a little very, very hairy caterpillar looking like shape. And it is going to be like it's going to be oscillating between a mean, and that is technically stationary right there. The reason why we want stationary data is so that the ARIMA could theoretically identify or predict on that stationary value because everything is within a certain range, whereas if it's not stationary, like this right here, where our data are just like skyrocketing up, our predictions are going to be completely off, and our overall model is probably going to be like junk pretty much. So this is one of the reasons why we want stationary data. Now, there are two ways to identify whether or not our data are stationary, and we could potentially just look at our plots and we want to see if we can actually make it like a really hairy squiggly caterpillar. And so one of the ways to do this is to use a diff function over here. The diff, as I mentioned earlier in this video, is that it's just taking a future observation and you subtract it with your current observation, and that's your difference right there. And this is what it looks like. It's not really surrounding the 0 in this case, the mean of 0, because we have very widely oscillating terms at the very end. So one way to do this is that we actually transform our data, utilizing the log function, and then with the log function, we just take the difference of that log, and we have more of a quote-unquote caterpillar. Ideally, these lags, these observations, would be closer to 0, but since this is real-world data, this is not like a simulated event, so we have to work with what we have. If there are other adjustments that we could do to transform our data using some really nifty algorithm, by all means use that to try to get like a more squiggly, a more tight caterpillar, so to say. Okay, so once we have this in terms of, it looks like it's stationary. The previous terms, if we just did one difference, it went all the way to 40 and then negative 40, and if we took the difference of the log, we're between negative 0.2 to 0.2. So drastic difference right there, and a huge improvement. The next step is to utilize ACF and PACF graphs. Now, this is the ACF graph. I just did par 1, 2, 1 row and 2 columns. And essentially what the ACF does here is that it lets you know however many parameters or the number of parameters to use within an autoregressive type of world, so an AR process. And we typically look at the number of values that are outside of this confidence interval or these bands that we have here. And this is where it gets sort of like speculative. There's not really one like solid great way to just look at a graph and determine however many parameters you need for a given process. So in general, if there are like at least one of these lags that are sticking out, then we can assume that we can start off with a base model of AR1 just for the ACF graphs. And note that what these bands signify is essentially that there is a statistical significance to a specific observation that's not equal to 0. That's pretty much what that is telling you. So if it falls outside of those bands, then it is saying that there is enough statistical evidence to suggest that that lag is not equivalent to 0. Hence, we would have to pay more attention to those specific points that are sticking on out. Also, if there are like some points that are sticking out toward the further you are away from the 0th lag, then that signifies a potential seasonality factor into that. But we won't really be getting into that into this video. Yeah, so if you are interested, make sure you comment down below and I'll do a video on that. The next graph is the PACF graph, and this is what we use to identify a moving average component. And similar to the ACF, we just look at the number of components that are sticking out. We also have to look at whether or not there is like some form of a shape curve, like an exponential curve, or like a sinusoidal wave. I don't know if a sine wave or a cosine wave, and that tells you if there is like exponential decay and stuff like that. But there are other structures that exist out there, but in this case there's not really much of an oscillating factor, so we don't have to take that into consideration. But if there is some form of a structure, then there is a really good starting point for specific values that we can plug into our ARIMA model to have like a good start when we are trying to compute what is our best form of our model compared to our previous models. Cool, so let's convert that back, standardizing the weights. And then when all of a sudden done, we have our given like ACF and PACF graphs, and we determined what is a good number of parameters to use. We want to figure out if our data are stationary, right? One of the ways to do this is use the ADF, or the augmented Dickey-Fuller test. And there's really neat functions in T-series where we just plug in the data that we plugged in for the ACF and PACF graphs. Now, the null hypothesis states that the data are not stationary, and the alternative is data are stationary. So since our p-value is less than 0.05, it is safe to assume that we reject our null hypothesis here, and we assume that this is true. Our data are stationary. So we passed our first phase. Now, our next step is to create our model now. So let's load in our forecast library, and what I have over here is our training and our testing data. So I'm going to be testing or training the data 5 years out up to 7 days from now, and our testing is going to be 7 days in the future. The same is going to be applied, the same number of dimensions for our external regressors for our training and our testing that's associated with our training price and our external price, or our external training. So I'll load that in, and we're going to be doing our fit. We can actually play around with our ARIMA model. We have over here, we can play with the seasonality, the order, etc. So our xreg is going to be our external regressors, and we can play around with the other values related to, you know, just like playing around with the background. But in this case, I'll be sticking with the default values, and let's run the fits, do the summary of the fit. Now this provides you the coefficients of the associated values that we have within our given data set. These are all the way up here. These are our external regressors, and these are the AR and the MA variable associated with our overall model. They also provide our training set score, and this just tells us like how well it's done when it's like training. So a really neat function or neat package is LM test. Really neat machine learning package where we could identify whether or not our coefficients are significant or not. And I just ran a COEF test, which comes from LM test. This tells us whether or not our given variable is significant or not. So in a previous video, I've done explanations about logistic regression, linear regression. We went in depth onto how to identify whether or not a variable is significant or not. But high level overview, if you have not already watched that, p-value less than 0.05 means that it is significant, like 3-year and the adjusted close, AMD, Intel, and Broadcom. So ideally, you would just keep those values within your model, and you might have a better result. So let us judge. Well, actually, first let's do the confidence interval. This provides a confidence interval of our given coefficients, and this tells you, you know, what type of values you can expect. 95% of the time that will fit between those given values over here. So one way to evaluate your model, you look at your ACF and your PACF graph of your residuals, and notice I just put residuals over here. And ideally we want all of our values to fall within the bands. Notice that our PACF graph did not do that, meaning that we probably have more room to expand with our given model. But one of the really neat statistical tests that you can utilize is the L-Jung box test. I don't know if I said that right. It might be L-Jung or just Jung. But essentially this tells you whether or not your model shows a lack of fit. And in this case, we want our p-value to be greater than 0.05, and let's see if that is true. Our p-value is not greater than 0.05, meaning that there is statistical evidence that suggests that our model does not show, well, it does show a lack of fit. So meaning our model might be crap, unfortunately. So we could potentially identify what might be a better model. I tried playing around with the seasonal factor over here, you know, forcing it to be seasonal, and I, you know, put in the external trains, and I put the training price in here as well, and I ran this, but to no luck, our p-value is still less than 0.05, meaning that our model does not show any signs of it predicting the fit. So that's very unfortunate. One way that we could potentially work around this is to just do like a grid search on determining the number of PDQ values that we can do when we are going to be playing around with our ARIMA parameters. Really neat tool here is the ARIMA auto.arima. And this is really, it's like basically like a grid search where you could essentially just plug in the max amount of variables that you could potentially go up to, and this will just keep on iterating throughout all of those variables until it goes through all the permutations and combinations, and it spits out the best model based on the AIC value. So let's run this. I already set up all the parameters. I made it so that there is a D is equal to 1 for the differencing, which we've done earlier. Max number of PQ values, excuse me, is 5 and 5. This is related to our original ARIMA. The capital P's and capital Q's are associated with the seasonality factor. Yeah, I just made sure that seasonal is equal to true. But notice that our best model with the lowest AIC value is ARIMA 010. So This means that our model is essentially trying to predict a random walk, which means that our model is probably kaput, unfortunately. So for the COIF test, we can look at what variables are relevant or not. It seems like the 3-year and the other adjusting closing values for our competitors, in this case, the AMD, Intel, and Broadcom, they play a major role in determining whether or not our specific values can go up or down, so related to NVIDIA's stock price. We do a confidence interval on that too. So just for laughs and yucks, even though we know our given model is probably not good, not great, this is just an explanation as to how to do ARIMA in R. So this is how you forecast. We got our forecast over here. We just plug in our model using the forecast a function from the library. We plug in our external regressors, so this is our test, our testing regressors, and we just predict 7 days ahead. And so I just stored these values over here, and then I just plotted it, and this is all of our historical data, and right at the very edge, right over here, I don't know if I can zoom in here, I don't think I can, but right over here, that is what our predictions will be 7 days in the future. So this is what we are predicting over here, and this was kind enough to provide a range on, what our observations will fall under for our predictions. So that's what that looks like, and we can do the ACF and PACF of our residuals. PACF does not look so great. Let's do the ACF. That looks, it looks okay, but overall, let's do the last but not least, the Jung box. Yeah, our model is not very significant in that, like, it does not show like a it does not show any like significance that our model could predict stuff. So there's definitely a lot of room to improve on. We can probably plug in more observations or different types of variables that are associated with trying to predict your stock price. So that is relevant to having your financial data, such as your cash flows, your income statement variables, your balance sheet stuff, that sort of thing. That might play an additional factor. You can also plug in some NLP related metrics as well and see if there's any change that goes with that. So there was a really neat library on metrics. I didn't really want to recreate the wheel, so I just did the RMSE of our training, of our testing values and our actual values. Had an RMSE of 6.31 and a mean absolute error of 5.21. So I found this to be really interesting. The MAE just suggests how far off we are usually from our given value. So in this case, you can read this as like dollar amounts. So at a given stock price for our NVIDIA stock price, we have like $500, right? Or 558 and 560. So this mean absolute error suggests that we are usually off by $5 within our forecast. So I thought that was really cool, and I hope that you can take that and probably improve upon that. I hope that you guys enjoyed this video on ARIMA. If you have any questions, please let me know down in the comments. If there's any additional content that you want to see, like ARIMA for instance, please let me know down in the comments as well. But this entire video encompasses the idea on how to apply ARIMA, the ARIMA model, with real world data such as the stock market. Now, I hope that you enjoyed this video so much that you leave a like, you subscribe, turn on those notifications down, and I will see you in the next video next week on a Sunday. So until next time, thank you for watching.